created a custom environment for reinforcement learning as a way of learning more about it. And I also implemented two reinforcement learning algorithms, DQN and PPO. When starting out, I couldn't find a lot of information about creating your own custom environment, so that's why I'm sharing my experience. I'll briefly go over the algorithm implementations, but I won't go into too much detail there. Here we have an overview of a single step in inference. We have a starting state, which we give to the agent. Then the agent picks an action and sends it to the environment. Then the environment performs that single step and returns an observation and a reward. This is the only type of interaction that we have with the environment. In training, the network training would happen somewhere around here, so after getting an observation and a reward. Let's take a look at the action space. So the action space is a vector of length 4, which means that there are 4 actions that the agent can take. We can accelerate, turn left, turn right, and brake. The observation space is a vector of length 9, consisting of 8 sensors, which measure the distance from the center of the car to the walls, and it also contains the speed of the car, and these values are all normalized. There are alternatives for the observation space. I use this one because it's easy and faster to train. But we could also use image data. We could get the pixel data of a rectangle around the car. And then we would just add some convolutional layers to the network, and the agent would still be able to learn how to drive the track. But because we would add some convolutional layers, the network would be slower to train. The reward structure is very simple. The track contains different checkpoints, and if the car drives over a checkpoint, it gains a reward point. And if the car hits a wall, it receives -1, and the car is reset. Some mistakes that I made with creating the environment the first time was the way I was handling the rewards. So make sure that you don't summarize the rewards within the environment. Only return the rewards that were earned within that one single step. You can sum the rewards outside of the environment, so in the training loop, and you can use that to measure performance. Also, it's important to make sure that the game works without displaying the actual game. So separate your game logic and visualization of the game. This makes training a lot faster. Then the environment could be improved by making the reward structure more complex. At the moment, the agent has no incentive to drive fast in the current setup, but this could be easily solved by adding a reward for driving above a certain speed. So if the car maintains a speed above 10 kilometers an hour, it gains 0.2 reward each step or something. Also, adding a big reward for completing a lap might also improve performance. Overall, the biggest learning point was the impact of the environment speed on training. I have a very simple game environment, and my network is also very small due to this simple game environment. But still, during training, most time is actually spent in the environment. And as the agent starts to improve, it will spend more and more time in the environment because it will perform more steps before crashing, or it might actually reach the maximum amount of steps before we go to the next iteration. So if you have a more complex game environment, even more time is spent within the environment. And I think optimizing it becomes a must. There might come a point where you have to create an environment that can be run entirely on the GPU. Here we have our action space, a list that holds all the cars, and we support different maps. We use this if we actually want to display the game. The reset function is called if a car hits a wall or when the maximum amount of steps is actually reached. Then the step function, which takes in the actions from the cars. It supports multiple cars in the environment. I didn't use this in training. It would have made training a lot faster. I did use it in inference to have multiple cars driving around with different policies. We start with a reward of 0. Then it performs the action. It updates the car and sensor data, and it checks if the car hit a wall. I don't actually use this variable anymore. Remove it. So don't mind this. If the car hits a wall, reward becomes -1. And here we check if we drive over a checkpoint. And if we do, the car gets +1 as a reward. Then for every car in our environment, we return the state, which is the sensor data. We return the reward from this single step. We do a hit wall check, and this does nothing really. I used this before because I actually had a finish line on the track, but I removed it, so that's why it's still here. And if we did hit a wall, then we reset the car. In our DQN module, we have replay memory. Here we save all the transitions. We have the DQN agent with policy and target network. And here's our network. Very small network, only a few layers. And input and output size are based on our observations and actions. So if you would use an image instead of the sensor data, you will get some convolutional layers before this, and the network will be bigger. And we have push memory. So here we have the state action, next state reward. So we use this function to push this information into the memory. Select action, update parameters. This naming is kind of weird, but I'll explain after optimize model what it does. Then when we look at optimize model, we start by sampling from memory based on our batch size, and we use these transitions to create batches. And we only want to keep the batches who have a non-terminal next state. And here we send the state batches through our policy network to calculate the values. So we get the state action values. Then for our target network, we calculate the Q values for the non-terminal next states. And then to compute the expected Q values, we use gamma to balance between the current or immediate and future rewards. Then here we have the Q values of the policy network and the ones of the target network, and we calculate the loss by using the mean squared error. So in short, our policy network is used as our main network, and we train it actively. So every step we send it observations and get actions back from it. Our target network is used to stabilize training. So we don't update it every step normally, you update it every n steps. In my implementation, let's go to the training script. Oh, this is the wrong one, DQN. So here in training, you don't actually see anything about when we update policy or target network. It just says optimize and update, but as I said, it's a weird function name. And I actually do update the target network every step, but it's a soft update. So it has the same effect as updating it every X amount of steps. Normally, after X amount of steps, you copy the weights of the policy network to the target network. But this is also one way of implementing it. So the target network slowly moves to the policy network. And our actor is responsible for the policy. It's the part of the model that decides which action to take. So it's the one that takes in observation, outputs probability distribution over all possible actions, and we sample an action from it, and then the environment uses this action. For a critic model, it evaluates how good the actions are by estimating the value of a given state. So these are our state and action pairs. It takes an observation and then estimates the output value, and it helps the actor to improve by estimating the advantage. Here we create our network as well. On initialization, we have orthogonal constant layers. This is to have a better starting point for training. Again, it's a small network. And here's our memory class where we store all our values during training. So when we look at the PPO training script, you can see that here for every step we send the output of the environment to the memory. And then after X amount of steps, we start optimizing the model. So in optimizing our model, the first thing we do here is we start by computing the generalized advantage estimations. And this step tells us the difference between our expected reward and the actual reward received. We loop back through time, as you can see here. So we go in reverse. And we do this to update our advantage, estimating the rewards and values stored in memory. And this gives us a better advantage estimation, which is then used by the actor. And as I said, we only do this after every iteration. So we run one iteration here. Then we optimize our model, and in our model, we traverse all the steps that were done within that iteration. This advantage, the generalized advantage estimation, helps us to determine which actions will give us the highest future rewards. Because we traverse the steps taken, so our last reward contains information about our previous rewards or our previous steps. So, and this is also known as the discounted sum of the future rewards. And here we use lambda as a smoothing parameter. So higher values of lambda give us more weight to future rewards, and lower values of lambda give us a bit more focus on the immediate rewards. Then we flatten our batch. And the reason why we use log probabilities is to increase numerical stability. If we don't do this, and if we would just use normal probabilities, if we would start multiplying them together, we get very small values, which makes it unstable. And also in log space, multiplication turns into addition, so it's also more efficient to compute it this way. Then we create our data loader, and here we start iterating over multiple epochs and mini batches of the experiences that we stored before. And here we don't want to deviate too much from our original policy. And the reason for this is to make training more stable. So we use target KL for this. And here what we do is we calculate, this is the difference between our old and new policy that we calculated here. And basically if the difference between between both policies is too big, then we stop updating. And then we start calculating our losses. We basically have two different losses. We have our policy gradient loss to update the actor network. And for a critic network, we have our value loss. We want to prevent large excessive policy updates. And to achieve this, we start by calculating the regular policy gradient loss here, followed by the clipped policy loss. And then we take the maximum and mean of both. And this is our new loss. Then for a value function loss, the value function is used to estimate how good a state is. And here we want to minimize the prediction errors. And we also have a clipped and unclipped version. Then when we calculate both losses, and then we want to calculate the loss that actually goes to our optimize function. And this is basically a combination. So we have our policy gradient loss to train the actor to maximize rewards. We have entropy loss, which encourages exploration. And we have our value loss, which is used to train the critic to predict returns accurately. And then we send this loss to our optimize function to update the actor and critic network. This is the moment you find out if everything that you implemented is working correctly. And debugging in reinforcement learning can be pretty hard. So I suggest to start with a simple environment. Even if your end goal is a complex environment, try if you can make a simplified version of it first. Solve that and then move on to a more complex one. To make sure that everything works, you can connect your own implementations of the reinforcement learning algorithms to a gym environment. Gym environment expects an action as input, and it will give an output like an observation and a reward. You'll probably have to change around the data types that you're using, but it's pretty easy to do. Then you can also hook up your own environment to a standard implementation of these algorithms. And this way, you can be certain that you didn't make any mistakes in your implementations. For the parameters, I would look at papers of the algorithms that you implemented and use those parameters. And you can also look at other people, their implementations, or people that have a similar environment to yours. For the network, I would start with a small network. This way, it's faster to train, and you can always go bigger. But the bigger network takes a lot longer to train. And if you have a very simple environment, you probably won't need a very large network. So start small, and if it starts overfitting, you can always make it a bit larger. It's also important to monitor results because you'll do a whole lot of training. So you need somewhere to store the results. You can create a simple version and just put everything into a CSV file or whatever. I put my results in weights and biases. So here are the results of all the experiments. I have some other pages as well. But you don't need weights and biases or other platforms. You can just write to whatever file you want and then create some graphs. But it's important to monitor because you'll do a whole lot of training and you'll switch around parameters, network size, or even algorithms. So make sure that you have something in place to monitor results and go from there. In my case, when I wanted to improve performance of the agents, I implemented random spawn points for the cars during training. This way, it learned to generalize more and it didn't overfit anymore. And also using random maps. Of course, this is highly dependent on what environment you created yourself. But it's important to get creative. Also, you can just read about people who have maybe a similar environment to you and see what they did to boost performance. Of course, you can play around with the parameters, with the network, but there's probably more to be gained with stuff like this or with changing the reward function. Some improvements that I could make. I have multiple agent support in the environment, but I never used it during training. Currently, I have around 10, 12-ish spawn points per map. I think increasing this number would also help. And during training, I only monitored maximum reward, steps, and mean reward. And I think using the loss as well and maybe some other metrics um, could have been very beneficial. Here are the results from my PPO and DQN implementation on a custom environment over 3 different maps. The mean score is the mean of the rewards of the last 100 training steps. And I tracked if static or random spawn points were used during training. PPO was trained for 4,000 steps and DQN for 6,000. Despite this, PPO outperformed DQN by a lot, as we can see. PPO almost always reached a score of around 400, and that seems to be the best it can do with the maximum amount of steps it got in the environment. When looking at the results, PPO performed better on 2 maps with static spawn points. So we can see here it does better with static and here as well. However, only on Scuffed Monza it does better with training with random spawn points. But when I run inference, the agents trained on random spawn points seem to do better and don't crash often. If we look at DQN's performance, it was pretty close overall. Only training with random spawn points reached a much higher peak on the last maps of Scuffed Monza, as we can see. PPO is designed to perform better on continuous action spaces, so it was expected that it would outperform DQN. Keep in mind that when running inference with DQN, it still actually does fine. A reward of around 80 or 120 is still multiple tracks worth of reward. You can probably get the performance closer on an environment like this if you play more with the parameters or change the network a bit. Anyway, that is it. Hopefully you learned something.